All right, everyone. Today I'm going to answer a question posted on Ask an Expert about finding a moment of inertia on a solid sphere. And that formula, 2/5 mr squared, is where our axis of rotation is through the center of the sphere. So if I have a sphere, we're saying that the axis is going right through the middle. So when this thing rotates, it's going to have an inertia, a resistance to movement, and that inertia is, we want to show that that is 2/5 mr squared. Okay. So what are we calculating when we calculate a moment of inertia? We're looking at a piece of mass, and we're asking how far is that from my axis of rotation. So that's like this D here. And we know that in spherical coordinates, this angle here is phi. And so D from this diagram is r sine phi. Okay, so that's the distance of that piece of mass from the axis of rotation. But what I have to do is I have to integrate over the entire ball. Okay, so we're going to use spherical coordinates. And I'll skip a few steps here, but I'll write I equals the integral. We know that we're going to have a theta integral, a phi integral from 0 to pi, and an r integral from 0 to r. And now my d, like I said, is r sine phi, okay? And the integral in general for this guy is the integral over some volume of r squared dm. So this is the general formula for moment of inertia. So here my d is r sine phi, so I square that. And dm is rho dv, where rho is the density. Okay, so what I have here is the integral from 0 to 2 pi. And then dv is the Jacobian, which is r squared sine phi times dr d phi d theta. So that's my entire integral, triple integral that I need to evaluate. Okay, so immediately what I'm going to do is skip a few steps. So I know that theta is not really involved in this function, so I'm going to just multiply the whole thing by 2 pi. And I know that r kind of stands alone, right? I can just integrate that guy. So in the front, I'm going to have 2 pi divided by 5 r to the 5th. And this whole thing is just multiplied by an integral over phi. And I'm going to have, I also have a density in front, rho. And that's just going to be sine cubed of phi d phi. Okay. Now this guy, what I'm going to do is I'm going to factor out sine squared, and I'm going to use the identity that that's 1 minus cosine squared phi. And then I have an extra factor of sine phi. So I'm skipping part of the integration, but this is a trick that we can use to integrate powers of trig functions. And then here, to evaluate this integral, you'll use a u substitution. Okay, so what we find when we evaluate this is this prefactor that comes from integrating over r and theta, multiplied by this integral, which turns out to be 4/3. Okay, you can verify that. And I'm going to break this into two factors. So I have 2/5. And then r to the 5th is r squared times r cubed. So I have r squared. And this is all multiplied by 4/3 pi r cubed rho. Okay. So this part if you remember the volume of a sphere, it's 4/3 pi times the radius squared, cubed. And if I multiply that by the density, I get the mass. So this guy underlined is just the mass. And lo and behold, we have 2/5 r squared. So I hope that this video was helpful, and I'll see you next time.